You are staring at a timeout. CPU is flat, the database is not hot, queue lag is boring. Retries are firing, but nothing looks on fire. So the room says slow network, slow vendor, slow disk. Pick one. That is the wrong frame. In agent systems, the timeout you see is often not where the wait starts. One worker holds a resource claim, asks another service for work. That work lands on a queue, a second worker picks it up, and the callback path quietly depends on the first claim being released. Every hop is alive. The system is still stalled. What you have is not slow code. It is a circular wait spread across processes.
Service dashboards are good at local truth. Service B says request time is normal, the queue says consumer lag is normal, worker C says it started on time. None of those panels answer the war room question: who is waiting on whom right now? Each team opens its own span tree, sees healthy work, and hands the problem to the next team. That is how phantom timeouts waste an hour. You're inspecting execution. The failure is in dependency ownership. The callback is waiting on a lock held upstream. The upstream worker is waiting on the callback result. In isolation, both sides look busy. Together, they are deadlocked.
This is where distributed context propagation stops being tracing hygiene and becomes evidence. You need the same trace across HTTP, queue messages, tool calls, and retries. Start with trace context, so every span shares the same trace ID. Then add the operating metadata you actually debug with: workflow ID, task ID, claimed resource ID, retry lineage, and who currently owns the claim. When the queue hop cannot keep parent-child shape, use span links instead of pretending it is synchronous. Now you can ask a useful question. Did this worker resume independent work, or did it pick up work that points back to an owner already in the path? Without that metadata, every retry looks fresh. With it, the loop stays visible.
Here is the reveal moment. Request R184 starts in agent A and claims resource L42. Service B schedules a summarization task. Worker C resumes that task from the queue and calls back into agent A for approval. The callback carries the same trace ID and a span link to the queued task. It also carries resource ID equals L42. That is the tell. The callback needs the same resource that agent A is still holding while it waits for worker C to finish. Your trace graph is no longer a line. It closes on itself. Once you draw wait edges, the timeout moves from mystery to proof. The slow-looking span is just where the loop became visible. You still need to separate bad latency from circular wait. Slow traces keep moving forward. A downstream call takes 8 seconds, but ownership changes, spans complete, and the dependency chain does not revisit the same claim. Deadlocked traces do the opposite. They revisit the same resource owner, often with retries that look like progress in metrics. That is why average queue lag can stay normal while a few workflows rot. Healthy slowness stretches the path. Deadlock folds the path back onto itself. If you want one operational rule, use this one. Slow work accumulates duration. Deadlocked work repeats dependency state.
The implementation beat is small but important. Propagate trace parent through every boundary. Put workflow ID, resource ID, and retry of in baggage or message metadata. When a worker resumes from a queue, create a span linked to the publish span. Then run one cheap guardrail before you take the work. If the incoming resource ID is already owned by any span or lease in the current ancestry, reject, defer, or route somewhere that can break the wait. Do not rely on timeout to discover this. Timeouts are expensive deadlock detectors. A cycle rule at the queue edge is cheaper and easier to explain and review.
Lock in 4 guardrails before the next page. Propagate context across every async boundary, not just HTTP.
Annotate resource ownership so traces can prove who held what. Cap retries and QTTL so stuck work expires instead of orbiting forever. Alert when a dependency graph revisits the same resource owner inside one workflow. That is the whole shift. Stop asking only which service is slow. Start asking whether the request depends on itself now. If the collector routing episode was about where telemetry goes and tail sampling was about what traces you keep, this is about keeping causality intact across the hop that usually blinds you. Drop a comment with the boundary that breaks context first in your stack: queue, callback, tool runner, or retry worker.